The failure of tissues and organs following disease or injury has been a thorn in the side of human healthcare for much of our existence. Before the second half of the 20th century, there were no sustainable remedies available to treat the impairment of organ function. However, in 1954, Joseph Murray altered the course of human history and revolutionized the treatment of dysfunctional organs by performing the world's first organ transplant. The kidney transplant was initially done between two twins, eliminating the risk of adverse immune response, though this changed 5 years later when the first transplant between non-genetically identical individuals took place. Since then, the number of annual organ transplants rose significantly, with over 153,000 taking place in 2019 alone. A significant majority of these were focused on the kidney and the liver. Shortly after the first transplant took place, the first human-to-human heart transplant took place in South Africa in 1967. However, unlike with either of the kidneys or the liver, heart transplants have taken longer to advance and have been met with difficulty. Initially, the one-year survival rate was approximately 30%, though thanks to advancements, particularly the appearance of the immunosuppressive drug cyclosporine, it is now over 90%. Despite the individual increase in survival rate, transplantation still faces challenges such as shortage of organs, cardiac allograft vasculopathy, malignancy, and drug-induced complications associated with chronic use of immunosuppressants. Over the years, a number of solutions have been presented to deal with the challenges associated with heart failure. These include tissue engineering, the use of artificial hearts, and the development of chimeric hearts, which will now be explored.
Doctor, how are the results? Will I be able to live?
I'm so sorry to break the news, but based on your current condition, I'm afraid your heart will stop functioning soon. Usually we would recommend a heart transplant from a donor, but unfortunately we're experiencing an organ shortage. I can still put you on the waiting list, but I cannot guarantee a new heart will get to you on time.
Doctor, please tell me what other options I have. I'm willing to try any options available as long as I can live.
I can refer you to the clinic next door and send them your report. I believe they might have what you're looking for.
Welcome to the clinic next door. You will be seen shortly.
Welcome. We have received a report on your current conditions, and I believe we can offer you 3 options. Please take a look at the menu.
3? What great news.
Well, first on the menu, we have a lab-grown heart. With technological advancement, we are able to grow a heart with the help of 3D printing.
Okay.
Well, not exactly the whole heart, but more for scaffolding. Instead of coloring, the printer uses bio-ink to print a scaffold that mimics the native extracellular matrix of a heart. The bio-ink will be a mixture of your cells and biopolymers that sticks the cells together and allows solidity in the scaffold. The scaffolding is tested to be biocompatible, biodegradable, and contains sufficient mechanical strength and electrical conductance. The best part of this lab-grown heart is we will be able to grow your heart using only your skin cells.
Skin cells?
Yes, by using a gene editing technology, we can change the DNA packing and expression level of your genes by treating your skin cells with transcription factors. This allows the extracted skin cells to be reverted back into pluripotent stem cells, and these are called induced pluripotent stem cells. Well, these cells will act as a building block for us to grow you an organ. As they are not specialized, we can program these pluripotent cells into any type of cell in the body. Over time, we'll be able to generate cardiac cells like cardiomyocytes from reprogramming the pluripotent stem cells. We then inject these cardiac cells into the 3D printed scaffolding to grow a heart. During the growing process, the heart will be infused with a nutrient solution while connecting to a bioreactor. This is to stimulate the heart, allowing expansion and contractions to happen by recreating conditions that are present inside a living human body. Over time, immature cardiac tissues will start growing and eventually being grown into a full organ.
I guess this sounds reliable and helpful, but how do you know my body won't reject this lab-grown heart?
As I mentioned before, cells used to generate the heart will be collected from your skin cells, so these are your own cells and DNA. Although we cannot guarantee no rejection at all, we can still ensure a much higher level of compatibility to lower the rejection rate. Moreover, before transplanting the heart into our patient's body, they will be stimulated by electricity to make sure it will start beating and perform a proper function of a heart.
Wait a minute, did you mention bioprinting a 3D scaffolding for my heart earlier?
Yeah, what about it?
3D printing is such an advanced technology. Will it be really pricey?
Well, if you're looking for a cheaper method of building a scaffolding, I guess we can go old school and use a donor's heart as a scaffolding.
So, how does that work?
Every year, there are organs identified as incompatible for transplantation. However, if we decellularize these organs by stripping all the blood and cells, leaving only the structure of the organ, and inject patients' own cells, these organs will be useful again. So instead of a 3D printed scaffold, we can use a scaffold from a human donor. What do you say?
Are you sure it's ethically safe?
As with any new technology, there are always concerns of safety and side effects. But thanks to the right to try law, anybody with a life-threatening illness or condition can try experimental options. If it is highly likely that they will not survive, it is better to try something new and risk any harm than do nothing and let patients die.
Okay, I'll consider that. But let me hear my other options on the menu.
Next option.
Another option is an artificial heart made from man-made materials. Back in the 2020s, they used to be used as a temporary solution for people nearing the end of life or as a bridge to heart transplantation, but recent technological improvements mean that these hearts are now a viable long-term solution. If your heart was less damaged, it would be possible to use a left ventricular assist device, which assists blood being pumped around the body. These have been used since the 1960s and are very successful, but provide no assistance to pump blood around the lungs. Instead, what you want is a total artificial heart, which completely replaces both of the damaged ventricles.
Well, how do they work?
There are a number of different devices to choose from, each of which works slightly differently. In the early 2020s, there was only a single commercially available device, CardioWest, which was pneumatically actuated using an external pump. This used an external console that could be used to manually adjust heart rate, blood pressure, etc. Since then, the pump has gotten small enough to implant inside the body, able to be powered by an external battery pack via wireless energy transfer. This idea was borrowed from an earlier artificial heart known as a biocore and reduces the risk of infection. There is also a small internal battery pack able to power the heart for short periods of time.
Reduced risk of infection sounds good, but I'm not so sure about manual control of heart rate. That sounds like a lot of work.
Another device developed around this time was the Carmat heart. It was originally quite large, but technological developments since then have reduced its size. It has the advantage over CardioWest of containing embedded electronics that allows blood flow to be automatically altered, allowing for a hands-off approach to blood pressure monitoring. The actual mechanism uses hydraulics to move a membrane that then pumps blood out of the heart.
That sounds much better. Is that the system you'd recommend?
The Carmat heart device is a good option, but it's worth considering the Bivacor system, which has only recently come onto the market. This uses a single chamber with a magnetically levitating rotor in the centre that uses the centrifugal force of the rotor to create flow. This means that there's only a single moving part, which increases durability and decreases power consumption. Similar to the Carmat heart, it is able to automatically adjust the flow based on your requirements, and the designers are working on reducing the size of the electronic components, which currently require a small bag to hold them outside the body. The best option therefore depends on whether you value reliability or compactness of the device.
What are the risks with this type of heart?
Nowadays, the risks of these devices are relatively low. When they were first developed, some patients experienced internal bleeding, but this only occurred because the output of the artificial heart was greater than they were used to. Since then, methods have been developed to determine the optimal output to eliminate this risk. The materials are specifically chosen to be biocompatible and reduce the likelihood of rejection. All surfaces in contact with the body are made of bovine pericardial tissue and treated with glutaraldehyde to ensure that the device remains biocompatible long term. Additionally, the devices tend to have a lot of redundancy in them, meaning that if one part of the device fails, they will keep working long enough for the system to be replaced.
Okay, so what are the advantages of this over tissue-engineered hearts?
The main advantage is ethical. Since the device is created from mainly man-made materials, there are a lot fewer issues than might otherwise accompany stem cell research associated with tissue engineering. However, there are still some ethical issues, as some people believe that this engineering will lead to human enhancement that's not needed. There's also the financial aspect. Not everyone is as fortunate as you to be able to afford this expensive healthcare, and people understandably think this is unfair, but I believe that it would be immoral to deny you this life-saving treatment just because not everyone can afford it.
Okay, I'll consider this option, but can I have a look at another one?
Next option. Whoop.
Some would say I've saved the best option on the menu till last, a chimeric heart.
What on earth is that?
Well, a chimeric heart is made from cells with 2 or more different sets of DNA, meaning that the host chimera has the genetic code to make at least 2 separate organisms.
So, what cells will my heart be made from?
It will be made from your human cells and host animal cells, which you have 2 options for, either a pig or a sheep, since they're the right size to create a human heart.
Which would you recommend?
If the choice were in my hands, I would go for the pig, since they've been used as a physiological model for decades, and they've been subject to extensive research into somatic cell nuclear transfer. To put it frankly, I wouldn't bet on your survival with a sheep heart.
How exactly would you go about making me a chimeric heart in a pig?
First things first, we would take a small sample of your cells in a non-invasive procedure. Although your cells are already differentiated, we'll convert them back into induced pluripotent stem cells using a technology developed all the way back in 2006. The cells are reprogrammed back into their undifferentiated states by adding a specific set of reprogramming factors to the cells.
Okay, so what happens after my cells have been made into stem cells?
The induced pluripotent stem cells will be injected into a pig blastocyst, which will be implanted back into the host pig. Then your cells, along with the pig cells, will divide and develop into a fully grown pig, with a mosaic of human and pig cells ready for your heart to be harvested and transplanted.
Surely my immune system would recognize the pig cells as being foreign.
That's a worry of the past. Back in 2022, they had only managed to develop chimeric hearts with 10% of human cells, but now we can use CRISPR to disable the pig genes involved in the development of cardiac cell lines. This means that the human cells take the role of developing the heart, so that around 99% of the cells in your heart will have your own DNA, and will therefore be recognised as self by the immune system. And just to make sure the remaining 1% of pig cells aren't recognised, we will also use CRISPR to turn off the pig genes that might induce an immune response and rejection when transplanted.
I'm not sure about this. The idea of pigs becoming humans seems wrong.
What you described there has been termed the yuck factor, where people are uncomfortable at the idea of the species boundary between humans and pigs being crossed. In the past, there were concerns about human cells contributing to pig brains and the pigs developing human-like thoughts. However, we now use neural-specific suicide inhibitors and CRISPR to prevent this. We also ban the mating of pig-human chimeras to eliminate the chance of any human cells in a germ lineage being passed on to offspring.
Are you sure this is legal?
Yes, until recently, the Human Fertilization and Embryology Act of 2008 prevented the use of human pig chimeras. Specifically, it prohibits keeping any embryo, including human admix embryos, for longer than 14 days or beyond the development of the primitive streak. Now the guidelines have been relaxed due to the ability of chimeric hearts to save lives in the thousands.
It may be legal, but are there any ethical concerns?
Luckily, we don't face any of the ethical concerns associated with embryonic stem cells, since chimeric hearts use induced pluripotent stem cells. However, there are moral issues with farming pigs for their organs, as they're unable to give their consent and are essentially being treated as spare parts for humans, so some people feel that human life is more important than that of an animal. Also, religious people may refuse chimeric hearts, since putting human cells into a different species may be considered acting God or changing what God created. Another concern people have with the chimeric option is that it makes you less human and takes away from human dignity, but like I said, only 1% of the heart will be consisting of pig cells.
Okay, but will the pig be well looked after whilst it's alive?
Yes, all animals used for research and tissue engineering are kept to high welfare standards. It is required by law.
Are there any advantages of chimeric hearts over artificial or tissue engineered hearts?
There may be a lower chance of rejection than the other 2 hearts, since the majority of the cells have your own DNA and the heart is biological, unlike an artificial heart.
What about any disadvantages to this type of heart?
Well, there's one slight disadvantage. It would take a while to develop your heart from scratch in the pig. How long do you have to live?
I have 3 seconds.
Coroner to room 5.
Ooh, more work for me.